Thank you. Welcome back, everyone. Today we are going to look at some of the performance aspects of programs, right? And we are going to touch some of the basic concepts, and we are going to also touch upon some tools which will help us understand where the bottlenecks are and how do we address them, right? Let's start with the background first, right? Um, when we talk about typical instruction execution, we have 5 stages: fetch, decode, execute, and memory access and write back. Right, in fetch stage, we access the instruction memory. It responds with instruction, and in memory access stage, we access the actual data memory. Right, for that we send the address of the data, and data memory responds us with the actual data. Okay, so there are 2 types of addresses here, one for instruction and another for data itself, right? And the instruction memory responds with a byte sequence, which we interpret as an instruction, and the data memory responds with a sequence of zeros and ones that we use as data. Okay, now typically the address of an instruction can be 32 bits here, and it might respond with 32 bits, which is like 4 bytes. It can be typically called as a word, right? The same thing, if we are shared an address of 32 bits, we respond with a size of 32 or 64, again based on the word size, right? Now these points depend on what's called ISA, instruction set architecture. Okay, now the size of the address bits is typically dependent on the maximum memory that we support. Okay, now till now, whenever we discuss about memory, it's mostly like a black box saying that, okay, there is somebody sitting there responding us with the data for the address that we have shared. Okay, now let's look into that a little more in detail, because when we are trying to run any application, the impact of the performance, impact on performance by the memory is very huge, and it cannot be neglected. So when we write programs, also, if it will be really good if we understand how the memory is organized in our system. Okay, now saying that, the typical view of a programmer would be that his or her memory is very ideal, meaning that it is very fast. It is as fast as the processor. It is very large. It means that whatever the size of the program is, it will nicely be available in a very fast memory, right? And we want it to be obviously of low cost, and we want it to be highly reliable, meaning that it should not be lost or somebody else has access to it, right? And we want it to support multiple queries at the same time, meaning that if we want multiple data items, the memory box, that the black box that we are looking at, should be able to supply the data in parallel, right? That's where the bandwidth part comes into picture. Now we also want it to consume less power, because it is just storing the data. The actual computation is happening at the processor, right? And requires less area is okay, because over the years we have shrunk the memory size from this huge, here you see an hard disk of 5 MB, and now we are at a stage where even a 1 TB of data can be stored on a small micro SD card. So area wise is not a big thing, because we are able to scale it, right? But what about the fast, large, low cost, and less power, highly reliable, and high bandwidth memory? How do we address these issues, right? So the processor architects have given us what's called, okay, before that, a quick point. Here, over the years, if you see, the processor speed has been increasing almost till 2005, where we moved from single core to multi-core, right? But still, if we compare it with the actual memory, the memory is very, very slow, right? This memory that we are talking about is the DRAM. Okay, now how do we address the moment we see this picture, the fast requirement of the memory goes out of the window because the memory by default is slow. So memory latency was an issue, and when we move to uh, uh, multi-core, or even this can be extended to the GPUs also, where multiple processing elements are requesting for data, and we need the memory to respond to them as fast as possible. So we want the memory which is having low latency and high bandwidth. Okay, so with that, okay. Dr. Praveen, are we recording it?
I am recording in my system, right? It's not a big deal.
Oh, okay. Okay, fine. Sorry. Earlier we used to get a heads up, so it's okay. I guess this is because of the login. Okay. Now, in reality, what we have is it's usually explained with an example, right? I assume that you are sitting in a library preparing for exams or some task at hand, and you're reading a single page at a time from a single book that you are holding. Maybe you will have a few books related to that topic on your table, but there will be a huge number of book racks with a lot of books in the library. So at any given moment, what we are doing is we are processing only one page at a time, right? So it and we are holding a few pages or a book with us. One moment. I'm sorry for that. So the book we are holding is we will not at a time read more than from one book, but we will keep all the related books at our uh, disposal so that we can access them fast. So in the same way, what we do is typically when we write a program, we do something similar. We access a relatively small portion of the data at a time, and even though our entire, let's say our entire array or any structure that you pick might be huge, spanning across hundreds of gigabytes, at any given moment we'll be accessing few bytes at a time. So based on this observation, right, which is called principle of locality, right, so there are two variants of it. One is where is temporal locality, meaning if we are accessing a data, it will be accessed time and again. Okay, so it is good to keep the data with us in somewhere nearby, right? Again, if we are accessing any data, the nearby locations of this data will also be referenced soon, means used. So if we are streaming through an array, and if the access pattern is something like we are trying to retrieve element at index 0, 1, 2, 3, 4, etc., means that when we are trying to access element 6, we know that the next access would be for 7, right? Or if there is a stride where we are making jumps of from, let's say, the first element to the second, or to the fourth to the eighth elements, etc., we still know where we would likely be going to the next data. So that is the spatial locality part. So based on this uh, observation, right, the system architects have given us a very nice arrangement of memory. But before that, let's dive and understand this temporal and spatial locality a little more. Right, here is a small code snippet. We are just adding the elements of an uh, array V. Okay, the sum is more like an accumulator. We are just going through each element of V, and we are adding it. So if we look at the accesses of this array V, we will start with the first element, go to the second, then third, fourth, fifth, so on and so forth. So it is, you see that there is a some notion of spatial locality here. Okay, now another example. here is where we are adding elements of a two-dimensional array, or let's call matrix for simple understanding. So we have two loops now. There is one loop for rows and another loop for column, and we are adding the elements of one row and all the columns first, then moving on to the second row, next row and all the columns, then the third row, all columns. So if we look at, if we try to visualize how the data accesses are happening, so first we'll access A00. Okay, yeah. Then A01, then 02, then 10, 11, 12, so on and so forth. Okay, so this is how our data will be accessed. Now, so the first we are going to the right, then going back to the next row, then scanning through that row, so on and so forth. This is how this way we are doing in a zigzag fashion, right? Another example again is where we are again trying to calculate the sum of these two-dimensional array, right? But here first we are going by column, then next column, etc. So here the access pattern would be 0, 0, 0, 1, 0, 2, then 1, 0, 1, 0, 1, 1, 1, 2, then 2, 0, 2, 1, and 2, 2. So if you look at the access pattern, we go down first, then top of the next column, then so on and so forth. So here too, there is some notion of spatial locality. Okay, now if you look at the variables I and j here, right, these will be typically stored in registers, but the actual array elements will be stored in some other memory elements. Okay, and the values n and m are also not changing, right? And if we bring them from the memory, we can keep it close and we can reuse it multiple times, saying that these can be visualized as having temporal locality in general. Okay, even the sum also has temporal locality here. We are using it time and again. Okay, and we can extend the same thing for the instructions themselves, because each of these is an instruction. Now, if we try to visualize that, okay, we are moving from instruction 1 to 2, then 3, right? Then I4, maybe I5, and let's say I5 is a loop, looping, or the branch or jump. Then we go back to I1 again. So here there is some notion of both temporal and spatial locality, both in the instructions and the data, right? So that's the summary, that programs tend to repeatedly use the same variables, and these will be having good temporal locality. And even if they have some stride, they'll still exhibit some spatial locality. Okay, and loops in general, when we write, will exhibit both temporal and spatial locality with respect to the instruction themselves. Okay, so to exploit this, the system designers have given us what we call as a memory hierarchy. So it's a practical and fast way, practical way to achieve a fast and large memory at a low cost, right? And it is heavily built on principle of locality, right? So it is usually represented as a pyramid, right? At the top, from top to bottom, as we go, the latency, meaning the time we need to get a data item, will increase. The capacity of the memory will be increasing, and then cost of the memory will be reducing, right? Now, how is this actually achieved is because of various memory technologies. Now, at the top of the pyramid, we have what's called registers, where frequently used variables are stored, like in the previous example, n, m, sum, I, j. These variables will be stored in registers, right? Following that, we have caches, and typically these are built with SRAM technology. Following that, we have main memory, which is built with the DRAM technology, and this is what we refer to when we normally say RAM. Okay, and then after that, we have the secondary memory, which is earlier built with magnetic disk or HDD, right? Now we have what's called flash memory, which is SSDs. right? The earlier micro SD card that I showed you is based on flash memory only, right? Now, just to give a quick understanding of why it is low cost, how we are able to achieve that is the semiconductor memory, the SRAM one, is typically very fast. It has few 1 to 2 nanoseconds of time to access any data, but is very costly, $500 to $100, $1,000 here, right? When we go to DRAM, it is having 10 times more latency, 10 or maybe here 20 times more latency. Okay, and its cost is almost 20 times less in that way, right? And then we have our SSDs, which are taking much more, thousands of nanoseconds, and it is quite cheap. Then we have our typical hard disk, which is very, very slow and very, very cheap. So that's how we organize the data, saying that at the top we have very fast elements like registers and caches, which work as fast as the processor. Then but then their size is very small. But as we go, we increase the size of the memory, right? Make it now few hundreds of gigabytes to terabytes also. Then we have the following that we have the secondary memory. Okay, so we have to thank our electronics engineers for helping us with these new memory technologies that have different latency access, latencies of access. Now, of late, we have new memory technologies like STT RAM, then we have PCM, etc. But the takeaway for us is we have higher memory hierarchies that are existing today. I'm sorry for the formatting issue. Seems like something is got up and down, right? So we have not one level of cache, but we have multi levels of cache here, L1, L2, L3, even some processors have L4 cache also. At the memory also, we can have multi levels, level 1 and level 2. Again, they can be some mixture of DRAM and PCM and STT-MRAM, etc. Right, the same thing can be extended to the secondary memory also. So this is how we are able to exploit the locality and get some reasonable memory hierarchy that can help us run the application as fast as possible and still hold large applications in their size, right? So if this we consider as a chip, we have it's a quad core chip. We have 4 cores. Each of them themselves have L1 cache. So these arrays are L1 caches. Outside of each core, we have L2 cache also. Then we have a common shared L3 cache, right? So we have L1 private, L2 private, and shared cache, which is common, right? Following that, we have an interface to the DRAM, which these are DIMMs, which we typically call as RAM. And following that, we have the secondary memory, right? Okay, so there is a question. Okay. So the price that I mentioned is in 2012. Yes. The same trend is continuing. In fact, their individual components have become much more costlier. Right. Only the storage has become cheaper, but the DRAM, if we go from DDR3 to 4 to current DDR5, it is still costlier, but still it is cheaper than the on-chip cache. So these memories which are lying on this chip are called on chip, and the DRAM and SSD are called off chip. Okay, okay, yeah, sorry. Right, and now who is going to move the data between these various memory levels? Right, we have registers, we have caches, L1, L2, L3, then we have memory, and then the storage. Now, who will move the data in and out of these, right? In manual arrangement, the programmer will move the data explicitly from the registers to the caches to the DRAM, etc. Right? And then we have another setting which is automatic, where the hardware manages the data movement. Now, manual setting is like now the programmers not only need to worry about the algorithm that they are implementing, the correctness of it, etc. They also need to visualize how the data is moving underneath, right? So it is very difficult for them to begin with, right? It is typically deployed in a few embedded processes where we have what's called scratchpad memory, which is visible to the programmer. But other than that, for all normal purposes, we do use automatic. On the other hand, if we are talking about GPUs here, we still do the data movement from device, which is the GPU, and host, which is the CPU, right, manually. Means the programmer will explicitly say, okay, move this data element, let's say the array, from the host to device or from device to host. Okay. Now, on the automatic front, the best thing is that programmer need not worry about how the data is moving or how the data is organized. So he can, he or she can primarily focus on the efficiency of their program directly, right? But then, if you want a program that is working faster than a naive implementation, it is always good to have an understanding of how the data is being arranged. So that is the primary motivation to introduce these memory, the notion of memory hierarchy, locality to you, right? So the same program, if you are able to run it faster, it's always good, right? Now, in a typical memory hierarchy that we have in modern day processors, it's something like this. We have a few numbers of registers, right? It can be 64 or 128. Maybe in some advanced process, we have just 256 registers, but nothing beyond that, right? And each register will have capacities to store maybe 4 bytes or 8 bytes. Okay. Following that, we have our L1 cache, typically few tens of kilobytes, right? And the movement between the registers and caches, right, is done by the compiler. It is manual in nature because somebody has written compiler to begin with. We are all using it, meaning the programmer or the program will explicitly move the data in and out of the registers. Right. Now, following L1, we have L2, which is slightly bigger in size and slower. It means that it would take few, tens of nanoseconds. Following that, we have a bigger L3 and slower L3. Now, between these L1, L2, L3, the data movement is automatic. Okay. It means that the programmer will not be doing anything explicitly for moving a word or an element from one level of the cache to another level. Following that, we have our main memory, and then we have our swap disk, or in general, we can call it storage. Now, the movement between the swap disk and the memory is done by the OS, right? It is a kind of automatic in the sense that the program does not do it. It has nothing to do with the working of the program to begin with. Okay. Now, from the main memory to the L3 also, it is still managed by the hardware. Okay. So from top, when we go down, it's generally what we call as abstraction. At various levels, we can abstract the way we are referring to the memory. Right. Now, this type of hierarchical arrangement is not only in our computer systems, but in general, everywhere we can find. Okay, so we have TLBs also, which follow multi-level TLBs followed by the page table. Then we have L1, L2, L3. These are all hardware anyways. The virtual memory, again, it's based on the TLBs. Then we have buffer cache, which will store small parts of the files, right, in the main memory, and it is managed by the OS. Right. Then we have disk caches, This is managed within the SSD or HDD, right, by the disk controller. It will cache on the frequently used data, right? Then on the network, we have what's called network cache, wherein parts of files are stored, which will be re-referenced, right? And then in our own browser, we have browser cache, right? A few frequently visited web pages will be stored, and their landing pages will be stored in the local copy, right? That's why sometimes even if you're not connected, at least the first page typically the landing page will be loaded quickly. But when you try to navigate from there, it takes time, right? The same thing gets extended to the data centers or web servers where we have web cache. Again, their entire pages will be stored for faster access. Okay. Now, if quickly before we dive in, a few points to note. Address is anything that is helping us refer to a location, okay, in the memory. So even if we try to visualize the data being stored as a matrix, right? When we say get me the data at location 3x3, 3,3, for example. So that 3,3 is the address, and the data it can store can be 1,000 also. Okay, so that is the difference. We will have to give precise location of the address of the data, and the memory will respond with the actual data that is residing there. Okay, then typically these memory levels can be inclusive in nature, meaning if we have L1, L2, L3, then whatever is there in L1 will be there in L2, and whatever is there in L2 will be there in L3. Then we say that they are inclusive in nature. Okay. Then in general, when we are moving data across different levels of the hierarchy, it is typically between two consecutive levels only, or two adjacent levels only, meaning L1 to L2 or L2 to L3, so on and so forth. We don't directly move data from L3 to the registers directly. Okay. Now, at the caches, the unit of transaction is typically a cache line or cache block, which is 64 bytes or maybe 128 bytes. At the main memory, we deal in pages, right? At the secondary memory, we can deal in terms of sectors or groups of pages, or which are called blocks. Okay. Now, as we go from the L1 to L2 to L3, all these are still talking to each other in terms of cache blocks only. But when we move to the main memory, we move pages. So it takes longer time for us to bring a page, which is typically of 4 kilobytes or 8 kilobytes from the storage to the memory, right? So why do we bring larger size chunks then? It is basically to exploit spatial locality. Okay, because the adjacent data items are possibly referenced again, right? So a few new terms. Hit is an event where we are finding the data in that particular level. Let's say there was a request from the processor to the L1 cache for some data. We take the address, we look into the L1. If the address is there, meaning that the corresponding data will also be residing, it is called a hit. If it is not there, then it is called a miss. Right now, a ratio of total number of accesses to the number of hits is called hit ratio. Now, to help you run your program faster, do we need high hit ratio or low hit ratio? Do we need more number of hits or more number of misses? Okay, so Malti has responded that we need high hit ratio. That is indeed correct, because if we are able to find data in the levels which are closer to the processor, it means that we are spending less time waiting for the data. Okay. Then miss rate is just opposite of hit rate. We need more hit rate and less miss rate, right? And hit time is the time we need to get the data if it is a hit. Okay, earlier the numbers I was showing that, okay, to access L1 we need 1 or 2 nanoseconds, to access L2 we might need 10 nanoseconds, etc. is typically the hit time. If the data is there, it will get it back in that much amount of time, right? Miss penalty is the time we need to get the data if it is a miss. Meaning, let's say we are looking up to the L1 and the data was not there, so it is a miss. Then we need to send the request or the address to L2 saying that, boss, I don't have it. Do please check. If it is there in L2, then it will be L2 hit, and L2 will respond us with the data. So the time L2 will take to look up to its own cache and figure out whether it is hit or miss, right? If it is hit, then it's good. If it is a miss, again, that will get forwarded to L3, eventually to the memory also. If it is not there in the memory, then it is called page fault. Okay, then the OS will intervene, then it will fetch the new page where this block is there from the hard disk, place it in the memory, then memory will respond to L3, then the response goes to L2, then eventually the data will come to L1, right? So all this latency is called miss penalty, right? So let me go to the next. The memory access time is the time a particular level takes from the moment it gets a request and it responds with data, right? Memory cycle time is the minimum delay between two consecutive requests. It means, let's say if L1 says, okay, I'm already working on data, so don't give me any more further requests. And it says, okay, wait for 5 cycles, right? So that 5 cycles is our memory cycle time. And typically we don't want such a delay between two consecutive requests. So L1 is typically able to handle multiple requests back to back, okay, with hardly 1 cycle delay. But when we go to lower levels of memory, they do take longer time. Okay, then we have terms called volatile and non-volatile, meaning if we switch off the power, right? If some particular memory loses the data, then it's called volatile. But if it retains the data, it is called non-volatile. Typically, our hard disks are non-volatile. Okay, but registers, SRAM and DRAM based memories, which are our registers, then cache and main memory are all volatile. Okay, the moment you switch off your system, all the data that is residing in them will be gone, right? And the term random access memory means whenever we are trying to access any data, irrespective of where it is residing in that memory, it will take the same time. Okay, meaning again, if we try to visualize the memory as a 2D matrix of, let's say, 1000 by 1000 size, right? The time we take to access the first element, which is 0, 0, and the time we take to access the last element, 999 cross 999, if the time is same, then we call that it is a random access memory. Okay, and our registers, SRAM and DRAM are random access in nature. That is the reason they are labeled as SRAM and DRAM. And our hard disk and SSD are typically not random access in nature. Okay, they do take a longer time if based on the location of the data. Okay, then read-only memory, I'll skip this in interest of time. Now let's look at the cache memory. So it is based on SRAM technology. I'll skip this. The hardware details of it. It is static because we don't need refresh. This point you'll understand better when we are discussing DRAM, right? It is volatile in nature and multiple levels of cache are common, right? Meaning that when the core sends an address, which first check in L1, if it is a hit, we respond. If it is miss, then we forward the request to L2. If it is hit, then it will respond back. If not, it will forward the request to L3, so on and so forth. Okay. And now the data transfer between the cache levels is at block level, and between the processor and the L1 is at word level. Typically word is 4 bytes or 8 bytes. So that is the size of your typical integer or float variable, right? So that is the access granularity between L1 and processor. So again, why we are taking an entire block which is 64 bytes or 128 bytes is to exploit any possible locality. Meaning, if we are declaring an array of integers, right? Each integer will take 4 bytes. And if the cache block size is 64 bytes, it means that one cache block will be holding 16 array elements. Okay, so A0 to A15, then A16 to A31 will be in the second cache block, so on and so forth. Now, what is the advantage of that is when there is a request for A0, we are not only getting A0, we are getting A0, A1, A2 till A15, and we are keeping it ready with us in a hope that the next future accesses might use it. Okay, that's where the spatial locality part is. If they use, then we will not incur miss, right? So that is what we want to exploit. Okay, now cache, how it works is it's typically a collection of blocks, right? And overall cache size is number of blocks times the simple block size. Okay, now if this is a simple arrangement on how we can visualize a cache of 8 blocks. Each block is having capacity of 16 bytes, meaning that it can hold 4 integers, for example, right? Word 0 is one integer, word 1 is another integer, word 2 and word 3. Now, each word is now collection of 4 bytes. So it will have byte 0, byte 1, byte 2, byte 3, so on and so forth. So that's how you can imagine the data is organized. Okay, and each cache block has an address associated with it. So here, for example, this particular block B0 has an address 1000, and the next block can have an address 3BEF. This is in hexadecimal, right? So on and so forth. So we will store not only the data, but also their address, so that whenever there is a request, new request that is coming in, we will know whether that particular address is available or not. Okay. So, let me, okay. So the portion where we store the addresses is called tag array. The portion where we store the data is called data array. So the cache will have explicit storage to keep the address and the actual data. Okay. Any questions so far? Okay, so let's move forward. Typically, the cache controller is the brain of this cache, you can say. Okay, there is a question from Malti. Is size of L3 greater than L1? Yes, it is. So that's how they are arranged. Okay, L1 is smaller than L2, L2 is smaller than L3, so on and so forth. But they're all still made with SRAM technology. The larger they are, the slower they are. Okay, then what about the number of address bits? So we are going to look at it, okay, in a short while. I'll address that. So let's now when we are saying that, okay, the cache is having tag array and data array, they are just normal storage elements, but who is going to access them, get the value that is stored, compare it with the request that has come and say that it is hit or miss is typically the cache controller. It is like the brain of this cache. Okay, the data array, tag array are simply dump components which are just storing the values. All the processing or all the lookup will be done by the cache controller. Okay. Now, when the cache controller will get an address, it will look at the take the address bits and compare it with the existing addresses. If it finds a match, then it's called a hit. Then it will respond. It will take the data from the data array and respond back, right? Else it is a cache miss. In that event, the cache controller will forward this request to the next level of the cache. Now, in general, it is a common practice to understand the overall cache operation using 4 questions. First is, where can I place a block of data? Is it that I can place it anywhere, or is it that I can place it only in fixed number of places, right? It is called block placement. Where can I find the block? Okay, I have stored it, but how can I retrieve it, right? That is called block identification. When the cache gets full, because the cache size is very small, when it is full, then I have to evict some block. Which block to evict is called block replacement. And what happens when we get a write request to the cache? So it's called write strategy, right? In interest of time, I will go through these questions a little fast, but I'm going to share detailed slides with you. You can check and get back, right? For the first question, where can I place the block, is if I can place it everywhere or anywhere, that is called fully associative cache. If I can place it only at one designated location, it is called direct mapped cache. If I have not the entire cache nor one particular, but there are few set of locations there I can place, it's called set associative cache. Okay, if there are n possible locations, then we call it as n-way set associative, right? Now, let's quickly understand how the blocks are mapped. Okay, let's say our memory has capacity of let's say 32 blocks. Okay, 0, 1, 2, 3, so on and so forth. This is 1, 0, 1, 1, 1, 2, so on, so forth, 30 and 31 blocks. Okay, that's the block number. This is our memory. Now let's take a cache which has capacity of only 8 blocks. Okay, it means that out of these 32, at any given moment, I can store only 8 of them, right? In a fully associative cache, okay, we are going to see all the 3 caches: fully associative, direct mapped, and two-way set associative cache. Now, important point to note is all of them have same capacity. Here, fully associative also can store 8. Direct mapped also can store 8 blocks, and two-way set associative can also store 8 blocks. Okay, now if we take block number 13, right, in a fully associative cache, this block number 13 can be placed anywhere. Wherever we find free space, we can fill it in. Okay, so it means that it has 8 possible location targets, but in direct mapped, it has only one possible target. And how do we find it? Is 13 modulus 8, because there are 8 blocks, 8 block capacity direct map. So it is 5th location, 0, 1, 2, 3, 4, 5. In the 5th location only, we can place this block. In two-way set associative, as the name says, there are 2 locations where we can possibly place this block. Okay, and how do we get it? Is 13 modulus 4, because there are groups of 4. Right, that would be 1, right? Either it can be placed in any of any of these 2 locations. That's why it's called two-way set associative, right? Now, okay, I don't know why there is a repeat here. Sorry for that. How can we place? How can we find the block? Is now using its address. So this is the answer to the question of Malti, right? Now we are looking at address. The cache controller will receive an address. It will split into 3 parts, which is block offset, index, and tag. Okay, so tag and index together are called block address, right? And block offset is a log of block size. And index is a log of number of sets or number of groups. and remaining bits are called tag. Okay, now let's say we have 40 bits of address that is coming to us, and let's say our block size is 16 bytes. It means that block offset will be 4 bits, 0 to 3, right? And if we say that, okay, our cache size is 128 bytes, then how do we calculate number of sets is based on the cache configuration, which is direct or set associative or fully associative. But if we want to just understand how many blocks overall can fit, it will be 128 upon 16, which is 8 blocks. Okay, now in direct mapped and two-way and fully associative caches, the number of sets will be something like this. In direct map, each block, there will be one dedicated one-on-one mapping kind of thing, right? So we will have 8 sets, and in so to identify one of these 8, we need 3 bits. Okay, so the index field is 3 bits, and the remaining bits, removing the block offset and index, will be 33 bits. Okay, so in the tag array we are storing these 33 bits, and in the data array we will be storing 16 bytes. Okay, and this is the address split, meaning 6 bits will be for tag, 5 bits will be for index, and 4 bits for bits number 654 will be for index. Bit locations in the address like 39 through 7 will give us tag. In the set associative cache, the number of sets will now be half, because it is two-way, so it will have 4 sets only. Accordingly, the index bits will be 2, right, and tag bits will be 34. It means that each of these tag array elements in two-way set associative cache will have 34 bits. Okay, and in fully associative, right, all of them belong to one set practically. So we need to store 36 bits in each of these tag array in a fully associative cache. Okay, now the important point to note is even though all these 3 are having the same capacity, right, the number of tag bits are dependent on the associativity. Right, now coming to the question Malti has raised, how will this change when we are moving from L1 to L2 to L3, right? Now from L1 to L2, maybe L1 is direct mapped, L2 is set associative map, right? Or another change that can happen is the size itself, right? Maybe L1 is of having is capacity is only 8 blocks, but L2 maybe is 16. Accordingly, the index bits will change, right, based on the associativity and overall capacity. Along with that, the number of tag bits will change. I hope I was able to answer your question, right? Now, let's quickly go to, okay, I think I'm going very slow, right? Let me, okay, oh, sorry. Let me go to the slide where we are talking about performance, okay? Now you understood that a particular data item can be present in the cache or cannot be present, right? With that understanding, let's look at the performance point. Where is it? Okay. So to understand the effectiveness of any memory level, or in general the hierarchy, we have a specific metric which is called average memory access time, AMAT, right? It is defined as hit time, means if a data item is available in the cache, how much time will we take to respond back with the data? If it is miss, then how much time are we taking, which is miss penalty, times the what is the miss rate, right? Ideally, what we expect is miss rate is 0. So AMAT is same as hit time, meaning that all the lookups to the L1 or L2 or L3 are practically hits, right? But that's not the practical scenario, right? Now, how do we reduce this AMAT? The lower the AMAT, the better, right? We should either increase the block size, which will help us reduce cold misses, right? Whether we can increase the cache size, but then the bigger the cache, the slower it will be. The hit time will increase, even though the misses will reduce, right? Associativity can be increased, but there is slight impact on the hit time also, right? We can employ what's called prefetching, meaning before a block is requested, we'll get it somehow. We'll do some prediction, etc., and bring it and keep it ready, right? How can we reduce the miss penalty? Is we will typically deploy multi-level caches. We'll prioritize read or writes. And how can we reduce the hit time? Is we will do fast lookup, right? That's the reason we have small and typically 4 to 8 way associative L1 caches, because the higher the associativity, the slower it would be, right? And do address translation faster. That's why we have TLBs. Okay. Now, if we extend AMAT to okay, so how do we understand this? Is the best case AMAT is that it will just take one cycle to respond to get the data, right? Now, if we have two different caches, which is instruction and data, then we will split the AMAT further. Okay, in interest of time, I'll skip that. So this equation says what percentage of instructions are accessing the memory and what percentage of data means the load and store instructions are there. And within the instruction cache, what is its hit time, miss rate, and miss penalty, and hit time, miss rate, and miss penalty of data cache, right? Now, this AMAT equation can be extended to any levels of cache. Okay, for L1, it is simple like this. For L2, we can extend it, right? Where we are actually expanding the miss penalty of L1, including the AMAT of L2. The same thing we can do, we can extend it to L3, wherein the miss penalty of L2 will be expanded to have L3 performance, right? Now, there are many hardware approaches to reduce AMAT. Like I said, the closer or the lower it is, the better, right? And again, in interest of time, I'll skip it. So, Praveen, is it okay if I take 5 more minutes because we started late? Okay, so I'll take that as yes. So let me quickly project a few slides. Okay. So this we saw earlier that we are trying to access the memory. Now we know that there is a hierarchy of memory, not single mega block, right? Now, if all the instruction and data access are hits, meaning that they are taking only one cycle, basically, right? Then the time your program will take to run is just the number of clock cycles times the frequency of your processor. Okay, but typically it's not the case. What we need to include is the memory stall cycles, meaning for how much amount of time we are waiting for the data at the processor. That is the overhead, right? Now, if we understand the memory stall cycles, it is actually total number of misses times the miss penalty. Okay, miss penalties is, again, if we use the number of if you replace the number of misses with the instruction count times the misses per instruction, right? This misses per instruction is given as miss rate times total number of memory accesses times the instruction count. Okay, so this is our overall memory stalls, which depends on how many instructions that we are executing, how many of those are memory access instructions, meaning load stores, right? And how many of them have missed in the cache, and if it is missed, how much time are we taking? Okay, Now, if we replace this misses per kilo instruction here, this is the normal metric that we use, MPKI. Overall, if we consider for the reads and writes separately, so this is how it would be. In interest of time, I'll skip this. So any questions so far? Do you see the importance of having a lot more hits in the memory? Any questions so far with the working of caches? I have explained at a very high level, right? Because of limited size, there will be the data will be present or will not be present, and we should increase the possibility of having the data as often as possible, right? The hits. Okay, I hope everyone is back. Brahmaya, you can take over.
Okay, sir. Kapil, please share your screen.
Is it visible, right?
Yes. All right. So here we are using two tools, like one is a perf tool and one more is JRAPL. Like we are using these two tools for evaluating the performance, like what factors affects the performance. Like one is perf tool, like we are using the perf tool for calculating the performance, like cache misses, number of cache misses and number of cache differences. So based on that, we can identify the like what are the reasons for cache misses, for all those things. So perf is a performance analyzing tool, and one more we are using is JRAPL. Like we are using this particular Java tool for calculating the Java programs running on CPUs with running average power limit. So RAPL means running average power limit. So we are using these two tools for calculating the perf tool for calculating the cache differences and misses, and one more uh, JRAPL tool for calculating the number of total power consumption of your Java program, as well as DRAM power consumption. Right. So we'll check the performance of like power consumption of a program along with the number of cache misses. So we'll consider some example. So first we'll go with
This
tree.
yeah, AVL. This is actually.
Yeah, AVL tree. We are going AVL tree.
And,
so here, first we need to consider perf statement. Like perf command, we can directly this is a Linux tool. It is available in the Linux platform. So directly we can use this perf tool. Just we need to install it by using simple command. And after that, we are getting the statistics of that particular by using perf tool, like total number of CPU cycles, L1 decache, load misses, and load misses, all those things we are getting by using this particular tool. So mainly we are focusing on total number of cache references to cache memory and total number of cache misses. And in order to use this particular JRAPL tool, we need to have sudo permission. So sudo, again, we need to specify the path where that particular files are available. We need to specify the path. And here I'm applying on AVL my test. So I'm using the AVL tree here. So initially, we are considering the number of threads. First one, 8 indicates the number of threads. So I'm running my program with 8 threads. After that, the size of the list is 2000. So I'm creating a AVL tree with 2000 elements. After that, I'm running it for 2 seconds. That is a 2000 is indicating 2 seconds. And next one, we are 50 represents the pre-fill size. Means whatever the data structure is there, total data structure size is 2000. Initially, we are creating a data structure with 1000, 50% of the elements. That is 1000 elements. Next one indicates 25. So contains operations 25%. Then after that, 65 indicates that. So 65 minus 25, whatever the difference is there, that difference indicates the total number of operations. And whatever the leftover part is there, that will indicate the remaining delete operations. So, and here, so when I'm running this particular statement, so here we are getting the total CPU cycles, all those things. Here, if you look at the last 2 lines, cache references and cache misses. So total cache, we are getting here total cache misses and total cache references. So total total percent of cache references means whatever the cache misses are there. When you look at the cache references are more and cache misses are less, right? So what is the percentage? So whenever CPU is fetching some data from cache memory, we are getting the 15.3 times percentage of we are finding the 15.3% of cache misses. Like when we consider the number of threads 8. Okay, now we'll increase it to 8 threads. Sorry, 16 threads.
First, let me clear it.
Right. So previously we are getting, whenever we are considering the 8 threads, the total number of cache misses percentage is 15%. Now, if you look at this particular case, like whenever we are considering 16 threads, same size, same amount of time we are running, and we are considering same pre-fill size. So during this particular period, we are getting 40.0% of cache misses. Right. So when compared to the 8 threads, we are getting the more number of cache misses when we consider the when we increase the number of threads. And here, if you look at the power consumption, like here DRAM is consuming the 150 watts, and total power consumption of this particular Java program is 403.7 watts. Right now, we'll increase it to 32. Right. So here, if we consider number of threads 32, the number of cache misses percentage is decreasing when compared to the 32. Right. So when we consider 32, at that time we are getting 40% of cache misses when compared to the cache references, and here we are getting only 35%. And power consumption also is increasing. DRAM power consumption is 237, and power like total Java program power consumption is 500. Right now we'll increase it to 64, and we'll see the difference in number of cache misses and number of power consumption. Right. So here, if you look at the power consumption, like whenever we are increasing the number of threads, power consumption is increasing. Right. So previously it is less. Now, whenever we are consuming 64 threads, we are getting 633 watts power consumption, and DRAM is 264. And here, CPU, whenever we are considering the 64 threads, so at that time, cache misses also reducing. So here, if you look at the cache misses, like it is only 32.495% of cache reference, like misses. Right. So means total cache references is like we are calculating this based on the total number of cache references and based on the cache misses, we are getting this particular percentage. Okay. Now we'll increase it to 96 threads. And here we are considering a number of threads 96. So my machine is capable of my machine is having 96 threads. So I'm using all the 96 threads. So here we are getting 34% of cache misses. So total number of cache references you are getting here, and cache misses, like total cache misses is 34% of total references. And here power consumption also we are getting around 618, and DRAM power consumption is 273. So here all these energy consumption is in terms of watts, kilo operations. And here, whenever we are designing any particular data structure, so our aim is to design a data structure such a way that it should consume less amount of power, means power consumption should be decreased. Like, and whatever the cache misses are there, like if you are developing any application, so we need to develop that application such a way that total number of cache misses should be less. So based on these two things, we can do the modification to our program and we can improve the throughput. Okay. So any doubts regarding these two? Right. So perf tool, we can directly use it in Linux. It is freely available in Linux platform. And when it comes to the JRaffle tool, in order to calculate the power consumption, we need to we can get it from GitHub repository. Like there is a JRaffle tool repository. So from that you can access it. Okay. Any doubts? So this is the source for a JRaffle tool. So from here you can download the source code and you can execute in your system.
Kapil, perhaps you can, just copy the link and put it in the chat box also.
Yes,
That
sir.
will help later. Right? And
When it comes to perf tool, directly you can install it from Linux tool, like command prompt.
So, Brahmaya, can you also explain this perf annotate command? Have you explored that earlier?
No, sir.
Okay.
Just we are using it for cache differences and cache misses. That's it.
Okay. Can I just quickly try it again? Just instead of stat, just write annotate once.
Yeah. Kapil, yeah. Instead of perf stat, change it to.
Yeah. Instead of stat, just put annotate. ANN OTAT. Yeah. Yes. And then just press enter. Okay. Okay. It is asking for options. Is it?
Yes, sir.
Okay. So it's supposed to give us the event counts. So I guess we need to feed the number of events or which events that we want to track. Perhaps. Okay. Okay. Can you just go down a little? What all events are there?
These are the ones, sir.
Only 4 or 5 days.
Oh, okay. Okay. Fine. I was just curious that they might be helping us track the, data transfer instructions also. That would help. Okay. Okay. Fine. Please continue.
That's it, sir.
Okay. So you're going to demonstrate it for other types of lists also, right?
Yes, sir. Now we are applying it for linked list, sir. Like previously we applied it for aviary tree.
Right. Yeah. Okay.
Yeah.
So actually, this is the list tester.
Yeah. Can you test?
Yeah. So this is pointing now for the lazy list. Okay, let me check it out. Just give me a minute.
Otherwise, minimize it. Go to the command prompt, type.
No, actually, I'm.
Yeah, list test.
Where is it? This is lazy list. Yeah. So it's currently.
So here we are
it's
using
currently lazy list. Yeah.
lazy list. Yeah, compile it.
Okay. So
So as like we discussed, like Praveen sir explained about lazy list in the last class. I don't know exactly which class it is. Like I think he explained about synchronization techniques. So one of the synchronization technique is lazy list. So in lazy list, what we are doing is, so previously what we are doing is we are direct. If you are going with if you are talking about coarse grain, in coarse grain, we are applying the lock on entire data structure, so which limits the performance. So that's why we're going with the next data structure called fine grain synchronization. In fine grain synchronization, so we'll acquire the lock on first node, then we'll go to the next node. If that particular required, if it is not required node, then we'll go to the next node. We'll acquire the lock on that particular node. Then till like that, we are moving till the required node. That is called handover locking. Means first node will acquire the lock. Then if it is not the required node, then we'll go to the release that lock on that particular node. Then we will go to the next node. Like that, we'll repeat the till the last node. So here number of locks are every time we need to acquire the lock and we need to release the lock. So it will affect the performance of that particular application. Next, we are going with the optimistic. So in optimistic, what we are doing is instead of acquiring the lock every time on each and every node, we are directly going to the required node and we are acquiring the lock. And next one, when it comes to the lazy list, so we are in lazy list also we are doing the same. We are following the same approach. So what we are doing is initially we are going to the required node and we are acquire the lock on that particular node. But here, what is the difference between optimistic and lazy synchronization is? So in lazy synchronization, so we are not deleting the node directly. So instead of that, we'll mark that node. So I means we'll delete logically first. After certain amount of time, we'll remove the we'll delete that particular node logically. So here we are applying the we are calculating the power consumption and number of cache misses for this particular lazy list application. Lazy list application in the sense lazy list data structure. So here when we consider the number of threads is 8, we are getting the DRAM power consumption is 136 and total power consumption of this particular lazy list program is 350 watts. And here, when you look at the number of total cache miss as percentage is 0.119, right? So if you look at the tree data structure, when we consider the tree data structure, at that time, number of cache misses are more. Like every time we're getting 30% or 40%. But here, total number of cache misses percentage is 0.119. when compared to the total, like it is a percentage when compared to the total reference misses. Now we'll increase it to the 16 threads. Now here power consumption is also increasing. Like initially DRAM consumption, DRAM is 120, now it is 194 watts, and total power consumption is 347. And if you look at the total number of cache misses, so as we increase the number of threads, total percentage of cache misses is increasing, right? So initially we are getting 0.2% of cache misses. Now we are getting 25.0 cache misses, right? Now we'll increase it to 32. So when we consider number of threads is 32, then power consumption is 188. So when compared to the DRAM, power consumption is less for 32 threads, and power consumption is 413 watts. And here also, if you look at for 8 threads, the cache percentage misses is 0.2. Now for 16 threads, we are getting 25% of cache misses. And here when compared to 16, 32 is having less number of cache percentages. Like it is getting 21% of cache misses for all cache references. Now we'll increase it to 64. Right. For 64, DRAM power consumption is constant. Like it is similar to the previous threads. Like when we consider 32 threads, almost we are getting the same power consumption for DRAM also. But here also almost similar for total power consumption. But cache misses percentage is decreasing, right? So for 32 threads, it is less when compared to the 16. Now for 16 threads, it is less than the 16 threads as well as 32 threads. Now we'll consider 96 threads. Right. So when we consider 96 threads, these are the total available threads. So here power consumption is almost similar to the 64 threads. So power consumption is decreasing when we increase the number of threads also. And here, if you look at the cache percentage, means percent of cache misses of all cache references is decreasing. So here, total number of cache references is 13, right? Next, now this is here we are considering lazy list, right? Now we'll apply it to the course list. Course list. Yeah, comment the lazy list object also. Yeah. Yeah, increase it to 8 threads. This is for one thread. Right. So here in lazy list, what we're doing is in order to perform any operation, either insert operation or delete operation on a particular node, we need to directly go to that particular node. We need to acquire the lock on that particular node, right? But here in course grain list, what we're doing is we are applying the lock on entire data structure, right? So if you are acquiring the lock on entire data structure, only one thread is allowed to acquire like enter into that particular tree critical section, right? So here when compared to the lazy list, when we consider the codes grain list, at that time total number of cache references, like total number of cache this percentage is 2.162% of all cache references, right? So here it is increasing, right? So there we are getting 0.2. Now we'll increase it to the number of threads to 16. And here power consumption is DRAM is 90 and total power consumption is 140 watts. Now we'll increase it to 16. All right. So here, if you look at the performance when we consider 60 number of threads, so at the 10 total number of reference, total number of cache misses percentage is 1.7. And here, like we are considering the power, like total number of references, but at the same time, if you look at the throughput also, like for whenever we are considering the number of threads 16, for this particular coarse grain list, we are getting the less performance, right? Performance is very less, right? But total number of cache misses is less. But always we need to get a better throughput. So at the same time, cache misses should be less. So here, cache misses is less, but the throughput is also less. So that's not the case. So anyway, like if you are decreasing the number of cache misses also, we need to get the efficient throughput, right? So now we'll increase it to 32 threads. All right. So in this case, whatever the DRAM power consumption is there, it is almost similar. Like total power consumption also very less when compared to the uh, lazy list. The power consumption is very less, and total number of cache references also here very less. 1.8 of percent of total cache miss. Like in lazy list, it is almost 25 or 20%. Right now, we'll increase it to 64 threads.
We are having even skip list also.
Yeah.
I'd like to show you can.
Right. So here we are having we are using it for 64 threads. So for 64 threads, so power consumption is almost similar to the when considered 32 threads, but cache misses percentage little bit increasing. Now we'll see the total percentage cache miss percentage for 96 threads. And here for 64 threads, the throughput is 0.07. Now we'll see for 96 threads. Yeah, when we consider 96 threads, the performance is 0.06. So when we increasing the number of threads from 64 to 96, our performance is decreasing. Previously, it is 0.07. Now it is 0.06. So when we increasing the number of threads in codes grain, like there's a bottleneck. Why? Because we are acquiring the lock on the entire data structure. So which limits the performance. Means it will act as a sequential data structure only. So, but here, when we consider 64 threads, the performance throughput is 0.07, but the cache miss percentage is 3.37. Now, when we consider the 96 threads, the throughput is 0.06, means it is decreasing by 0.01, but cache misses also is decreasing at most by like 1.5% or approximately 1.5, right? Here, cache misses percentage is decreasing, but we are not getting the enough throughput. There is a problem here, right? Now, we'll apply it for skip list. Here, compile. For 8 threads. Right. when we consider 8 threads and the size of the skip list is 2000, and if you are running for 2 seconds, and 25% is contains operations, and remaining half of the percentage is insert, and remaining is delete. Right now, if you look at the throughput is 8.0 MOPS. MOPS indicates that millions of operations per second. So throughput is 8.8 MOPS, and power consumption of DRAM is 183 watts, and total power consumption is 400. Right, so here it is consuming more power when compared to the coarse grain list. And total number of cache misses is 23% of cache misses of all total cache references. Now we'll consider 16 threads. So when we consider 16 threads, throughput is increasing. So previously it is 8.03 MOPS. Now throughput is increasing it to 8.9. So during this time, power consumption is also increasing. Power consumption of DRAM is increasing, as well as total power consumption is also increasing. And if you look at the cache misses also, so percent of cache misses also is increasing, right? So total cache misses percentage is 42.22, right? So here, if you look at the when number of threads is 8, total number of cache misses, total number of cache references, and when we consider number of threads 16, total number of cache references is nearly same, right? So there is a small only difference, right? But if you look at the cache misses in when we consider 8 threads and when we consider 16 threads, there is a drastical difference in cache misses. So that is affecting here, right? So because of those cache misses is here more, that's why we're getting the less, more number of cache misses, right? We'll increase it to 32 threads.
Yeah, and even the size is also very small. Actually, we have taken only 2000.
Yeah, 2000.
As an input. Okay.
Right. So here we are considering 32 threads. So for 32 threads, throughput is increasing. So previously we are getting throughput is 8.9 MOPS. Now when we consider 32 threads, the throughput is 9.1 MOPS. So throughput is increasing, and power consumption also is increasing in terms of DRAM as well as total power consumption. And when we consider, if you look at the total number of cache misses, so here a percent of cache misses is decreasing. But if you look at the cache references, for 16 thread, cache references is less. But when it comes to the 32 threads, total number of cache references is more. At the same time, cache misses is very less. So that's why we're getting the 36 percent of cache misses when compared to all the cache references. Now we'll consider 64 threads.
I think if we run for the 16 threads once again, the cache misses may decrease.
Java VM also affects these cache misses, all these things. Yeah, run it for 16.
Okay, that's perfect. So,
yeah, it is almost similar. So, but the throughput is increasing. Like, see, whenever we are running any application, we need to run it for 5 to 6 times, or 3 to 5 times. So we need to consider the average of all those runs, and we need to consider average of all those runs, and we need to consider that particular average. Then only we'll get. Why? Because sometimes our cache will be affected by different applications. So because of that, our performance may decrease. So we need to run it for 3 to 4 or 3 to 5 iterations, and we need to consider the average of all those results. And 62, right, when we consider 32 threads, the performance is decreasing here. Performance is 5, like previously we are getting 10, right? Now we'll increase it to 64 threads. Right. So here, when we consider 64 threads, performance is increasing, like, but it is less when compared to the 16 threads. Here we're getting 8.8 and power consumption is almost similar to the previous cases, but here cache miss percentage is decreasing, and total number of cache miss references are increasing, but cache misses are decreasing. So and if we consider 32 threads or 64 threads, it is almost similar percent of cache misses. That is 34.2% of cache misses when compared to all the cache references. And now we'll increase it to 96 threads. Right. So here, when we consider 96 threads, so 96 threads during this particular thread count, we are getting the throughput 12.105. So here, if we look at the total number of cache references and cache misses, so cache misses percent is very less. So here we need to see whatever this percentage is there, this percentage is of like that 34.2 percentage of cache misses is total number of references. From total number of references, we are calculating the total percent of cache misses, right? But here, if you look at the cache references for 96 threads is more, right? So from that, when we compared with these total number of cache misses, uh, when we compared with the total number of cache references, cache misses is very less. So that's why we're getting the better throughput in this particular case. But if you look at the 64 cases, so we are getting total number of cache misses is 848 something. Is that right? So that is the cache references, right? So from that we are getting the 289 cache misses, right? That is the total number is there, right? So those are the cache misses. But if you look at this thing, like when we consider 96 threads, total number of cache references is there is more, right, when compared to the 96 threads 64 threads cache references. So here cache references are more, but when compared to with when we comparing with the number of references, cache reference misses is very less. So because of that, here we are getting the better uh, throughput. So previously we are getting 5 or 8 or 10. Now we are getting the, when we consider 96 threads, the performance is 12. So here, based on these, when we compare all these applications, whenever cache references are more, or when compared to the cache references, misses is very less. That at that time we are getting the more throughput. Means, so if the required information is available within the cache memory, we can get it in 1 unit of time. So for example, we can get it in 1 unit of time. So if it is not available within the cache memory, then we need to go to the main memory and we need to get that particular information. So at that time, it may take 5 units. Let us consider 5 units of time. So if it is taking 5 units of time, then it will take more amount of time to perform the operation. So because of that, it will affect the performance. So whenever the data is available in the cache memory, so then it can perform within 1 unit of time. So it will take less amount of time when compared to the cache miss. So whenever cache miss is there, it needs to get the information from the main memory to cache memory. So here, based on these things, so what we can say that whenever we are increasing the number of cores, so power consumption is increasing. So it's not true for all the applications, but when we look at if you look at the coarse grain list, for coarse grain list, performance of power consumption is similar for all the threads. Why? Because at the time we are applying only one thread on that particular data structure. But if you look at these coarse like lazy list or AVL tree or skip list, whatever the power consumption is there, it is increasing the power consumption, right? And when it comes to the cache misses thing, so if the cache miss total number of cache references is less, sorry, whenever like when we compare the cache misses with total number of cache references, if cache references are more and cache misses are less, at that time we are getting the better throughput. So if cache misses are more less, we are getting the more better throughput, right? So any doubts regarding these applications? Like we applied the perf tool and JRaffle tool on AVL tree, and then we applied on skip list and one more is linked list. Any doubts? Is it clear? Like, let me know if you have any doubts. Okay, then, thank you. Kalyan sir. Hello, sir. Hello, Kalyan sir. Wait for 2 minutes. He will be joined.
Okay, hope I'm audible. Right. Thank you, Ramya and Kapil, for walking us through the perf and JRALF. Right. So for the participants, right, these are very simple and effective tools to quickly understand how good we are, right? And if we are losing out too much on the because of cache misses, then probably it's better to go back and uh, implement your data structure in a more cache friendly way, right? That's what Dr. Praveen and even Brahmaya have talked about and demonstrated, right? uh, so in the same lines, when we are talking about caches, right, typically if we have a single application running on a single core, right, the cache behavior is predominantly understood by using three types of misses. One is cold, other is conflict, and third is capacity, right? And cold misses are those which will occur whenever we are trying to access a data item which was not accessed before. Okay. Now, conflict, as the name says, we have to, in a particular set, because it can, even if it is fully associative, or if it is set associative, let's say 4-way, right? If all the 4 ways of the set are full and we need to place one more block into the same set, right? Then we need to evict one guy. And if whomever we have evicted, if that was referenced again by the processor, right, then we have incurred an additional miss, right? That's called conflict miss. Now, the capacity miss, as the name says, because we cannot have the entire data all the time, it would be the additional items, the data items that we are not able to store, will be accounting for capacity. These are the normal 3 events that we can potentially see for a cache miss. Now, when we consider multiple processors, in a multi-core kind of setup where a single application might be running on multiple cores in a parallel fashion, or multiple applications, different applications can be running, one on each core or something like that, right? There we have a couple of more design issues with the caches, right? Let's look at them, right? Again, we are touching on these because they also have heavy impact on the performance. Okay. Now, on the symmetric multiprocessor setup, we will have one or more processors, right? Each processor can have, multi-threaded application, multi-threaded supporting core within itself, etc. Right? Each processor will have one or more levels of cache, right? Followed by uh, a shared cache, wherein the data of different processors will be present in the shared cache. Following that, then we have the memory, and then the main memory, and following that we have storage. Okay. Now, these caches which are um, within each processor, they are called private caches, and the one which is common to all of them is called a shared cache, right? With the private caches, the misses that I have just told, the cold, capacity, and conflict misses, will explain their behavior. But when it comes to shared cache, now because we have multiple cores, we will have requests from more than one core, creating, kicking out the data of another core, etc. Right? So let's see what type of issues might be there. Right? The key property in SMPs is that all the processors will have same access latency, right? Uniform access latency. Now, on the other hand, we have what's called distributed memory multiprocessors, right? There we the memory that we are talking about, right? It can be the L3 cache also, or anyone below that, the main memory, etc. They are all distributed, and one core, if it is accessing the memory which is local to it, right, it will be much faster. But if it is trying to access data from a remote core, remote memory location, then there will be longer latency. That's why we call this setup as non-uniform memory access. Okay, if the memory chunk is co-located, it will be faster. But if it is located in a remote location, then it will be slower to retrieve that data. Okay, now in these NUMA type of setups, the interconnection network will also have a say on the data access latency. The more the traffic on the interconnection network, the higher the latency it would be to retrieve some data item, right? Now, in multi-core architectures, the main issues would be that typically, how do we divide a program into multiple equal threads, right? It would be, the speed up would be completely limited based on the parallelism that is available. There are some programs which are embarrassingly parallel, like our matrix multiplication, convolution, etc. Right? But there will be some applications which are which have limited parallelism. So our job as programmer is to at least expose the available parallelism to the hardware. Okay. Now on the cache front, we have a new issue which is called cache coherence. Now, because multiple threads are running on different processes, right, and each can modify the data in its private cache. Now, how does that be reflected to the other cores, right? That is a bigger issue, right? And then we have memory consistency issue, meaning that a particular data item has been updated by, let's say, processor 1 and processor 2. And let's say we have two more processors, 3 and 4. Both 3 and 4 should see the changes in the same order, that the first write to this data was done by processor 1, then write was done by processor 2. Right? So this ordering of memory operations is very key. Only then we can ensure correctness of the parallelized execution. Right? Then we have shared memory synchronization issue, like that that I think Dr. Praveen and Brahmaya have earlier discussed also. Logs, barriers, we deploy them, right? And then shared resource management, how do we do better? Because now the cache is being shared, the interconnection is being shared, how do we manage them, right? Now, with the caches, right? If you remember earlier, I mentioned a point where multiple cores are there, we still expect the cache to support many requests in parallel, the bandwidth part, right? In the single core or for a single threaded application, it's not an issue. Hardly 1 or 2 requests might come to the cache in a single cycle, but in multi-core setup, there can be 10, maybe 10 requests will be coming to the cache. So how is that? How is it able to handle? How do we schedule these requests from different cores? Do we treat them equally, or do we take them, based on age, or is there some other criticality, etc. Right? Now, cache space is limited, so accordingly bandwidth is limited. How do we manage? And how do we design caches in a multi-core system? That is also a design point, right? And there can be many decisions, like whether this particular cache level should be shared or private. Now, how do we maximize the entire system performance? In that, what role is cache playing, etc. Right? And like I said, if some requests are there with higher priority, maybe it is because of the OS level information, or the user himself has said that, okay, this application is of utmost important to me, we need to accommodate such requests, right? And other cache management algorithms like partitioning, etc., will need to be looked at. Okay. Now, so private cache, shared cache, of course, you all know now that for a private cache, only one core will be accessing the data within it. For a shared cache, there can be one or more cores which will be accessing the data. Right? Now, for private caches, the discussion is more or less straightforward, but for shared caches, the issue becomes tricky. Right? Now, for what are the advantages of shared caches is the effective capacity usage will be higher. Meaning, if we have let's say 2 MB of private caches, and maybe one application is using only 1 MB of it, but the other application might require more than 2 MB. But because we went with private caches, even though 1 MB of one core is underutilized, we cannot use it. But if we have a shared cache of, let's say, 4 MB, then most likely the second core, which was requesting for more than 2 MB of space, might get benefited. So that's what this term means, effective utilization of existing capacity, right? Then accordingly, we can deploy some dynamic partitioning also. Maybe some core which is requesting, which is happy with less cache space will be given less space, and the one which is requesting more can be given more space, right? And it is also easy to maintain coherence that we are going to observe next, right? What are the disadvantages is it will be slower in access because there will be multiple cores which are requesting data. This guy is single entity who is trying to satisfy everybody. So your request will get queued up there, right? And because the actual hardware is shared, meaning that the space is entirely being shared, there can be inter-core interference. What it means is one core can kick out the data blocks of another core, right? This might sound similar to the conflict misses, but these events will increase with the number of cores, right? And guaranteeing a minimum level of service, meaning that, okay, I will be able to complete the execution of a program by so and so time, the maximum bound, etc., will be very tricky to ensure in a multi-core environment. Because now the execution of my program, the speed will not only depend on my program, but also the other co-application which is running. If that is having high memory usage, then I will get very less space in the cache. Accordingly, I will run slower. So these kind of issues need to be addressed, right? Now, so the same thing here we are trying to highlight. So let's say we have processor core 1 and 2, and core 1 is running thread 1, right? Maybe it requires some 3/4 of the L2 space, right? In the same way, maybe core 2, which is running thread 2, is also requiring 3/4 of the space in L2, right? Because of this, there will be cache sharing issues which will slow down most likely both T1 and T2. But if we somehow know that, okay, T2 is important and we give higher priority to it, meaning that we will not evict the T2's blocks in the cache, then T1 will get affected very badly, right? So these fair usage issues will be there, right? And this is just an example of how a multi-core processor might typically look like, right? So we have 9 cores here. Each of them have their own private L2 chunks, and L3 cache is kind of distributed here, right? So L3 is now split into banks, right? We have 1, 2, 3, 4 banks here. And again, the core, this is kind of a NUMA kind of setup where if a core's data is available in the nearby bank, then it can access faster. Otherwise, it needs to go to some other bank over the interconnection network. Excuse me. So let's come to the coherency aspect. If multiple processors want to use the same cache block, right? How do we ensure that they see the same consistent state? Now let's try to understand that. Let's say we have two processes, processes P1 and P2, which have private caches, and then we have the memory, right? Now let's say P2 has executed the instruction load R2X. X is the location of the location in the memory, which is having current value 1000, right? R2 is just an example register, which is again local to P2, right? So P2 has loaded value 1000 in R2. After some time, let's say P1 also has executed the instruction. So it will have a copy of 1000 in its own R2. Now later, if P1 has changed the value. Okay, again, here we have add R1, R2, R4. Let's say R4 has 1000 and so we add the value R2 1000 and R4000 and update this 2000 value in the same location X. Now what happens is this store instruction will go and update the local cache of P1. Okay, that's the reason we see 2000 here and 1000 here. Now the private caches of P1 and P2 have different values. That's what coherency problem is. You know, all the processors should see the same value. If they are not, then we say that they are not coherent. In that case, running any parallelized application is nearly impossible. We cannot ensure correct results, okay, in such a hardware. So how do we handle this, right? If we continue the discussion at a later point of time, if P2 has loaded the same location X into another register R5, it should ideally get the value of 2000, but because memory is not again updated, it will still again get 1000, which is wrong. You know, there is a correctness issue here. So when do we say that a memory system is coherent? Is when a location, when an data that is being read by one and modified by that one, that modified value should be reflected to all the other processors, right? And when location X is read by P1 and it is it is updated by P1, then if some other processor requests, then it should get this newly written value, right? And then writes to the same location. Let's say in the previous example, P1 has written some value, P2 has written some value. They should be reflected in the same order also, right? And then if we add the interconnection delays, right, then we have the memory consistency issues on when can the written value be seen by the next processor which is trying to read, right? And then we have the point that a write does not complete until all processors see the effect of that write. Meaning, if one processor has updated the value, all the other processors, if not the updated value, at least should know that the value has been updated. So that's what a coherent system should do. The second point is the processor does not change the order of any write with respect to any other memory access. Okay, so this is the consistency part. For a given location, all the processors should see the reads and writes in the same order. Not a single processor should not see anything different. Okay. Now, who is responsible to ensure coherency? Is it software or hardware? You know, if it is software, can a programmer ensure coherency? Because caches are not visible to him, it's nearly impossible for him to handle this, right? Accordingly, we can say that, okay, if some additional instructions are given in the instruction set architecture, maybe compiler will be able to handle it. So there are some instruction sets which support a local flush, global flush, flush cache kind of instructions that will help us maintain the coherency, right? Again, it is done by the at a compiler level, but at the hardware, it will take the burden from the software or software developer, right? If it is ensuring it. In coherent multiprocessors, caches provide both migration and replication of shared data. Okay, migration is when we are moving, replication is when we are copying. Okay, now there are few basic but very powerful schemes that enforce coherence, right, which we call cache coherence protocols. And the main key is main point is to track the state of any block that is being shared. Okay, So they are broadly classified into two. One is directory based, wherein a global directory will be there, which will keep track of all the blocks that are currently in the cache that are being shared, right? So in SMP kind of setup, we have this directory which is centralized, but in a distributed setup, then we can the directory itself can be distributed, right? In the other type of protocol is snooping based protocol, wherein there is no separate directory, but rather the cache itself will maintain some additional information to track the status of the block, right? So in the cache, we already have status information for the block. For example, its address is stored. We will know, we store one additional bit to say whether it is valid or not, whether it has been written or not, physically dirty or not, right? And then to enforce replacement policy, we need additional bits, right? All these can be grouped under metadata. Now, in coherent caches, which are following snooping based protocols, we'll have some more additional bits to maintain this coherency information, right? So a combination of these two is also possible, right? In approach one, we again in snooping itself, we can have potentially two approaches, which is write invalidate, right? Let's quickly walk through that. Let's say if processor A reads a location X, right? What we see on the bus is that there is a miss for X, right? Then processor B is requesting for X. It also sees a miss, and processor A writes 1 to X. Then the contents of the processor B will be invalidated, okay? And the contents of the memory location also will be invalidated. That's why it is in red box, right? Then when later processor B is trying to read the updated value of X, that's when the private cache of A will update the private cache of B and the actual memory. So at this point, all the three will see 1 in their respective private caches and the shared memory, okay? So A is called owner here. It is his responsibility to update other guys when they have requested, right? This write invalidate protocol works well for write back caches, right? And in interest of time, I'll skip here. The second approach is where we have update or broadcast protocol, meaning when one processor is reading, okay, there's let's say a shared memory location X is there, both A and B are trying to read it. A reads it away, so its local contents will be 0. Then B reads it, then both A and B local contents are 0 and 0. When A writes to X, let's say it has changed 0 to 1, right? Its private cache will be 1 here. And at that point, it will broadcast on the interconnection network saying that, hey, I'm updating this value X to 1. So all of them will update their individual local copies. So these are the two differences. This is the main difference between write back and update based protocols, okay? And what happens in this is in the next time when processor B is trying to read, right, it can potentially experience a hit because it already has an updated value. Earlier in the previous approach, right, it was a miss again, okay? So this kind of setup will work really good if we have a write-through cache, wherein all the writes at this level will be reflected to the lower level also. The previous approach will work for write-back caches. Okay, but the major disadvantage with broadcast protocol is that whenever a particular processor updates its local copy, it will broadcast onto the interconnection network. So the interconnection network will get flooded with these update requests. Accordingly, the write invalidate protocol is more prominent. Okay, snooping based protocol, a simple implementation, right? We will go with invalidation based, meaning whenever somebody is updating the local copy, it will just go and tell the shared cache level saying that, hey, please note that I have updated my local copy and whatever copy you have is stale. So that's what we call as invalidation. Okay, typically the bus will be used, and okay, let me directly go to the simple implementation. Okay, so how do we find a block if it's a miss in the private cache? Is the required block will not always be supplied in the memory, because some other private cache might have its updated copy. So the requesting processor will place the address on the common interconnection network, and the other processors will notice the address and will check their private caches. If it is a hit, and if they have the local updated copy, then they will put the updated copy on the bus. So that way the memory also will update, and also the other processes which have this cache block will also be updated, right? And there are some, let me quickly go to the simple implementation. So an example protocol is each processor will have a controller, right? Controller will respond to the requests from the processor and requests from the bus and interconnect also, right? And it will this controller is actually the cache controller itself. It has additional duty of maintaining the coherence. So it will observe the request from the processor, it will observe the traffic from the interconnects, and it will respond accordingly, right? What it will do in response is it will change the states of this block, right, or update. Now there is a big action item list for what event will be there and all. So I'll explain this simple MSI protocol. Okay, so it has three states: exclusive, shared, and invalid, meaning a given block can be in one of these three states. Okay, if the block that I have is in exclusive state, then I can read or write the way I want. Okay, this is in the private cache. That's what we were going to see, right? If there is a mess for this particular block, then we go to the memory and get it, and get it and keep using it. Okay, now if there is a write mess for the block, then we go to the invalid state, saying that okay, we need to fetch it from the memory, and the moment it comes back, we will go to the exclusive state or shared state the way we would have requested. Okay, so these kind of detailed protocols are very well in implementation, right? So this is what we saw is a MSI. Then we have extensions of MSI, which is where we have an exclusive state. Of course, earlier one is a modified state, right? And then we call it as MESI protocol. Then we added one more state to it, owned state. So we call that MOESI protocol. Okay, and Intel predominantly uses MESI with a slight change with it, and AMD Optron uses MOESI protocol. Okay, so now you see the additional work that the cache controller is doing, and the additional misses that can potentially occur because of this coherency issue. Okay, so with that, I will conclude today's lecture, and I'm open to take questions. Any questions from the participants? Okay, in that case, we will call it a day. Okay, we'll see you day after tomorrow. Thank you. Oh, okay, there is a question that I think I missed. 1 second. Okay. Oh, thank you, Malti.